So I look forward to your defense.
Great. I don't think I said that.
I have witnesses.
Has your clippers in his bag, right?
All right, so I'm going to be talking about real-time and robust robotic motion planning, particularly by leveraging massive parallelization, so GPUs, and through improving sampling strategies. If we look at what we see in the field today with robotic systems, it's things like robotic arms, which are operating in very well-known environments with well-known states, doing repetitive tasks. We have some drones starting to be in places like agriculture, where it's fairly simple, open environments. We have warehouse robotic systems that are leveraging some of the structure of the warehouse and how well-known their environment is because it's been set up for them. And then we start to see some self-driving cars where, again, they're leveraging the structure of the road very heavily, and they're behaving in sort of a conservative manner. When we start to move into the field, we find out the real world is pretty dynamic. It's unknown, unstructured, sometimes high-dimensional. So we have this humanoid robot as part of the DARPA Robotic Challenge. So this was a couple years ago and pretty much the state-of-the-art in a humanoid robot. And it just barely misses the door grab. It's not robust to this and falls over. And there's probably 50 videos of similar things on the internet, all from the same challenge. So across the board, we have issues with robustness on these very high-dimensional, dynamically complex systems. And then we have self-driving cars. So this is the Google self-driving car collided with a bus, mostly because it failed to realize how it was going to interact with the bus, thinking the bus was going to stop for it, and it wasn't, but also because it wasn't robust enough and maybe just didn't reason about the environment well. So I'm working on kind of laying the foundations to these problems, not necessarily solving completely these, but laying some of the foundations of robustness, of planning quickly in order to solve them. If we look at something like a delivery drone, which we heard about 6 years ago and still haven't really seen, we want it to be able to move something like this. And a key challenge towards that is to autonomously compute robust motion plans in real time, so very quickly, even in realistic environments, not too simplified environments. And we want to push it to the limits of the dynamics of the system, so not conservative. Now, the motion planning problem, Marco kind of quickly said what it was, but essentially we're trying to get from some initial location to a goal region and to find some sequence of actions to lead our trajectory between them while staying in the feasible space and avoiding any obstacles. So, we want to stay away from these regions and stay within here. In general, this problem is p-space complete, so pretty difficult. And the state space can be topologically very complex and very high dimensional. Here, it's pretty obvious where the solution is. It's not very complex. You can see the whole state space, but if we see something like the piano movers problem, which is sort of a canonical example of motion planning, we start with this piano here, and we want to go over here. And the path is, maybe clear. It wants to come through here in terms of X and Y, the position. But say it has to start going over things, or we start having to turn the system. It's a 6 degree of freedom system. It's got 3 rotational and then 3 positional. And it turns out the state space blows up pretty quickly with any sort of clutter or anything around it. So that's before we even consider robustness, before we consider differential constraints that we might really need to consider for a real system. Now, to visualize what the state space looks like, even on these simple problems, so we have a kinematic arm with 2 degrees of freedom. As it moves through the state space, red is a non-feasible position. Basically, it's in collision with the obstacles. And you can see this is pretty nonlinear, pretty unintuitive that this is what the state space looks like. I didn't know it was going to look like that until I basically plugged it into the software. And then in this case, we have a robot with an X, a Y, and a theta position. And we can see what the state space, it's pretty complex. It's not necessarily intuitive again. You can see the top makes sense. It's basically the outline of the obstacles when it's in one configuration, but the rest of it is difficult to reason about. So what I'm going to be talking about are motion planning algorithms, particularly global motion planning algorithms. So we want to solve the entire problem from A to B, not something local. One way we can do this is combinatorial motion planning. Basically, we construct a graph of all of the structure of the state space. So we completely represent our state space. And here you're basically identifying the vertices and then solving some shortest path algorithm through the graph that you've constructed. As the problem gets higher dimensional, more complex, these pretty much blow up. So 2-dimension, 3-dimension, they're probably better than what I'm using, but for anything more complex than that, they start to break down. So instead, what we use are sampling-based motion planning. So about 20 years ago, we realized that instead of specifically constructing the necessary structure, we can implicitly represent the state space through a set of probing samples. So we lay a bunch of samples down in the free state space. We then try to connect to nearest neighbors, check is there going to be any collision there, and if there's not, then we add it to a graph, and we make this graph that we can then search through. So they're either graph-based, like probabilistic roadmaps, or tree-based, like rapidly exploring random trees. They actually work very well for high-dimensional, unstructured, and complex spaces, and they give us probabilistic theoretical guarantees. So as we randomly put samples down, we'll converge to a truer representation of the state space, and we'll get probabilistic completeness, meaning that with high probability as the number of samples goes to infinity, we will return a solution if one exists, and then asymptotic optimality, which says that with high probability that solution that we return will converge to the optimal. There's also some extensions for differential constraints here, and so just to make it pretty clear what sampling-based motion planning is, so I'm going to go through the probabilistic roadmaps algorithm. We lay down a bunch of samples through the free state space. We then connect to nearest neighbors. We attempt to make all the connections to nearest neighbors, and if they're in collision, then we don't add them to the graph because it's not a feasible trajectory. We then end up with our final graph, which we can search to give us our solution. Now, what this looks like in practice, so we lay down a bunch of samples. We check if they're in the free space. We then try to connect to our nearest neighbors. So here we try to connect to nearest neighbors. We cut out any ones that fail the collision check, and we slowly build this graph as we add more and more samples. So in this is probabilistic roadmaps, so we're basically just doing batches of samples at once. And it really relies on just these three algorithmic primitives: probing samples, so checking if they're in the free space, checking their nearest neighbors, and then doing a collision check. And slowly we start to kind of converge on what the true state space looks like. At first, the implicit representation was not enough to really capture all the structure, but you can start to see it's this maze-like problem. And around here at maybe 1,000 samples, we start to get full connectivity of the graph, and then it just gets better and better as we add more samples, moving us towards a more optimal solution. So this was the planning problem. So what I'm going to be talking about today are how can we improve the samples, these probing samples that we put down. Generally, they're put down uniformly and randomly. Well, if we don't want to do randomly, it turns out we can use these low dispersion sampling sequences so we can actually spread out through the state space better and leave less uncovered regions, and also leverage a few other things that I'll discuss. And then in terms of uniform sampling, it's nice because it gives us these theoretical guarantees that we're going to converge to a true representation of the state space. But in this problem, it's pretty clear where the solution is going to be. So we should really focus our samples in those regions while still maintaining some bed of samples throughout the whole state space. And then I'm going to talk about real-time planning using GPUs. So simultaneous localization mapping updates sometimes at 100 hertz, 10 hertz, in that range. Our controller updates around 100 hertz. And we want to look at how we can use GPUs to make plans update at that rate too, leveraging the most recent information. And then robust motion planning. So a traditional algorithm assumes a deterministic, perfectly known system that's going to be able to follow your trajectory. But we'd really like to consider uncertainty during it, and ideally realistic uncertainty that we would see in the real world. So these are several papers that I wrote or was a part of, and I'm going to start by quickly discussing the sampling strategy work and then go into a little more detail on GPUs and robustness. So the question we asked was, we have probabilistic roadmaps, rapidly exploring random trees. Is this randomness, is this probabilisticness really necessary in order to get these theoretical guarantees and the practical performance that we've seen? So can we de-randomize these algorithms? Because if we can leverage a lot more offline computation. We know where the samples are going to be. We can compute like nearest neighbors. We can ideally certify some of our results that we will definitely find a solution. We can simplify some of the operations. Nearest neighbors pretty much is trivial. If you're in a grid, you know exactly what nodes are next to you. And then we can leverage some good deterministic sequences, which I'll show next. And what's been shown in the past is that de-randomized probabilistic roadmaps is resolution complete. So as the resolution goes to infinity, you will return a solution, you will return a feasible solution. And we've also seen that this has pretty good practical performance in terms of finding a solution. But some recent results in sampling-based planning have focused specifically on finding an optimal solution. So we wanted to ask, what about in terms of convergence to an optimal solution? Can we still find that with these de-randomized sequences? And then are there other practical or theoretical benefits, or practical and theoretical benefits to this? So a good sequence, it turns out, we're going to find the L2 dispersion. So essentially, we're trying to lay down these samples to understand the state space, the largest uncovered ball radius that we can put within the state space. So that's the largest area that we have no sample in to really understand. If we look at random ones, it turns out this dispersion, as we add more and more points, goes with log n over n to 1 over the dimension. But there also exist some low dispersion sets, so an obvious one is a grid that covers the state space better and actually removes this log n factor. So we can get 1 over n to 1 over the dimension of dispersion. And so you saw this in that video earlier, how the random built it. So with 500 samples, it hasn't fully connected its graph to be able to solve all planning problems. And then at 5,000 samples, there's still a lot of open regions. With a low dispersion set, though, we actually cover pretty well. There's no huge areas, and with 500 samples, we're able to solve pretty much any planning problem that would be posed within this state space. So first, looking at theory in terms of optimality. So for IED random samples, we get convergence to optimality and probability. So we have this probabilistic guarantee that with high probability, we will converge to the optimal solution as you add more samples. With low dispersion, deterministic, it turns out we can actually deterministically guarantee that we're going to converge to the optimal. We can also look at convergence rate. So the previous result of convergence rate was actually out of our lab in 2013, I think was when it was first posed. And you can see it's kind of a complex result. We have, it's a probabilistic guarantee. With low dispersion sampling sequences, we can actually guarantee it probabilistically and with just this simple statement of, that's in terms of the connection radius, so what area we're looking to connect to nearest neighbors, and in terms of the dispersion of the set. So we've got this deterministic optimality and convergence, a lot simpler. It also extends, it turns out, if we want to add some randomness, so maybe you want to perturb a few points to remove some of the structure of the sampling set. As long as you have deterministic low dispersion, we still get those guarantees, even with random points.
So Brian?
Yeah.
Are you going to tell us, there must be an algorithm or procedure for getting this low dispersion sample set? Are you going to talk about how to
I'm not, but basically you could just define a grid throughout the state space. So whatever dimensions we have, just put a grid down over it. Okay. But there's also some low dispersion sampling sequences like, so this is actually Halton sampling sequences, okay, which uses, it just spreads out the points well and has a guaranteed dispersion bound. But yeah, I'm not going to, It basically just relies on any sort of low dispersion sampling sequence, of which several exist. And these can also be used for hemodynamic planning or non-uniform sampling. So basically saying as long as you have a bed of low dispersion sampling sequences that are going to converge, you can still get these convergence rates and this optimality. And ideally, it's a step towards certifying our motion planning. What about in terms of complexity? Well, it turns out that a normal sampling-based motion planning algorithm attempts to connect to all of its nearest neighbors within some connection radius. For IED random sampling, this connection radius has to scale with log n over n to 1 over d, so basically that dispersion term that we saw earlier. With low dispersion sampling, we can actually scale this more quickly down. So it can go with n to 1 over d times the connection radius, just goes to infinity. So it's basically just barely above n to 1 over d. And what this means is we can reduce the complexity. So for every n points, we don't need to check as many nearest neighbors. Normally you had to check this log n number, and you have a complexity of n log n. And here we can actually reduce it to little omega of n. It also gets rid of all of these nearest neighbors computation as long as it's kind of automatic, where you, in something like a lattice, if you know where your nearest neighbors are going to be. And that's commonly a bottleneck. So there's several papers just discussing how nearest neighbors becomes a bottleneck in certain problems. And if we can remove that, we open up that whole kind of class of problems. In terms of practical results, so we ran this over a whole suite of test cases. We have rectangular mazes, we have rectangular obstacles, spherical obstacles, kinematic chains, we have kinematic arms, some rigid bodies, and then some dynamical systems. And what we're going to look at here are the number of samples required to get to solving 90% of the problems, the cost of the return solution at a medium number of samples around 1,000, and then the cost of the return solution at like 5,000 samples. And we're looking at the ratio of deterministic to random. So, I mean, as you can see, green is good. It basically, anything below 100% means the deterministic are outperforming. In terms of success rate, that's really where we see pretty big benefits. Sometimes we're seeing an order of magnitude fewer samples are required in order to find a solution 90% of the time. We're also solving the problem with almost always better solutions. In general, about 5% benefits are seen over all these test cases. But a key question is, so we've got we've been uniformly covering the state space, but a lot of problems don't actually uniformly use the state space. If we look at a robot like this humanoid robot, when most of the time it's walking, it's in gait, you don't need to consider the entirety of the state space because its operation is in a very small region of it. If we look at something like this planning problem, you pretty much immediately know where the solution is. It's going to lie somewhere around the initial and goal point. It's going to go through these narrow gaps. It's going to avoid obstacles. So the key to this was that we should learn a distribution from either previous solutions or from just seeing the robot operate, and we should then bias the sampling through that distribution to really stick to the areas that the robot would operate normally. In this case, we use a conditional variational autoencoder, and this technique allows us to use pretty much any system with it. So we can get very general, high-dimensional systems, which I'll show later. Some of the previous approaches will either do adaptive sample batches, so they solve the planning problem, and they only sample in regions that can improve the solution. It turns out that doesn't work or it's difficult to define what area improves the solution if we have these differential constraints. It's also possible that the solution is very circuitous and then anywhere can improve the solution. Others use workspace biasing, so they look at the obstacles and then they try to bias towards narrow passages or nearby obstacles, areas that we want to get more definition in. Again, it's not really clear how this works for high-dimensional or differentially constrained systems. And then finally, most recently, someone used a GAN to learn local actions, but in this case, it was just a very local kind of reactive policy for planning, not in this case, for us, we're doing full global planning. So I'm going to go through a case study of how this works. In this case, with a double integrator system, so basically a mass with force control, and solving this narrow passage problem. We start by taking our planning problem, our training data, which is a bunch of solved planning problems, though that again could also be robot operation or human demonstration of showing where solutions are. We decompose it into a conditioning vector that we're going to condition our distribution on. And so we do the initial position, the goal position, and then an occupancy grid. Though, again, it's very general. It could have been the actual obstacles. It could have been a picture of the planning problem, a lot of things. And then we train it to basically learn the distribution of points that were part of the successful motion plan. So this is a standard architecture for the conditional variational autoencoder. I won't go too much into it, but we're learning this conditional distribution of where we think sample points were placed. So with pretty much no training, it's just the zero mean Gaussian perturbed by the initial weights. But pretty quickly, it starts to converge. Oh, that's how. To pretty much dead on the solution to the planning problem. So this was in less than 10 minutes. We converged to sampling exactly through these narrow passages, everything that and respecting some of the dynamics.
Brian, what was the training data? That seems very important. If you already have examples of good trajectories, then why not just copy the good trajectories?
So the idea here is to both plan with less samples and to just plan faster. So once you have the fewer samples, and as we'll see in a minute, basically we can use an order of magnitude fewer samples here. And it means you can speed up your planning process by, again, an order of magnitude or so. And it also helps a lot. It helps a lot the convergence in terms of the cost coming down to the optimal solution because it's seen a bunch of, but yeah, in this case, we need to have been able to solve the planning problem. But in other cases, so if we wanted to apply it to that humanoid running around, we might not be able to solve the planning problem initially, but we can watch it just move through the world, learn to sample exclusively from standing, walking, good positions, and then solve the planning problem with that. And then if we want, we can plug it back in with these solutions and get better and better distributions as we go.
I think his question was more, what's the difference between the train set and the test set?
So same problem, but completely different, like initial conditions and, yeah.
Okay, so you get specific
So yeah, so say maybe we show it like 1,000 solutions, and then we give it new problems.
When you say solution, do you mean just feasibility or optimality?
So this is with an asymptotically optimal planner, but with just a certain number of samples, so it's a pretty good, it's a near optimal solution.
Okay,
yeah.
And you give instances of start and goal positions? Just
so we give it...
And generalize to new...
Yeah, so we give it start and goal position and whatever the obstacle set looks like, okay. So through that occupancy grid, and then we give it some new problem, some new problem that's never seen before.
Okay.
Yeah, so we are generalizing to a new problem. Otherwise, yeah, exactly, we would just... We actually had a reviewer who thought the same thing, so apparently we're not clear enough about this.
It wasn't me.
Yeah, so yeah, new ones, we're solving, this is now the online part of the algorithm where we get some new planning problem. We just want to solve it quickly. And again, we just decompose the problem into our occupancy grid and then to our conditioning vector and sample directly from the latent space of the variational autoencoder. And in the end, we get some distribution that looks like this through the middle. But first of all, I've been harping on all these properties of how it's nice to have some uniform coverage, how we converge to the optimal. We want to be able to maintain these theoretical benefits. And also the learning algorithm might miss by a bit, might have mislearned something, might get confused. And so we actually augment the number of samples, or the samples from this, with some bed of uniform samples at some rate. And so we get this good coverage, but also really focusing on the area of interest. And then what it looks like in practice, so this is a fast marching tree with, again, a double integrator system. We have a high density of samples in the tree going through here, pretty much all from the learned distribution. You can also note that the samples are pretty much always facing in the right direction. So it's actually learned to come in perpendicular in terms of velocity to to each narrow passage. And in terms of success rate, how fast does it solve the problem? It turns out, so these are learned at different ratios of how many uniform to how many learned samples, but it's pretty much the same, versus a uniform. So uniform might take 1,000, whereas here we're solving it in 100 to 200. We're basically an order of magnitude less samples, and we're able to solve it 90% of the time. In terms of cost, we converge immediately to pretty much optimal because it's seen so many plants. It's really focusing in the important region. Whereas this is a pretty standard convergence curve that we would see with uniform. As you add more and more samples, it slowly builds from a factor like 2.5 times suboptimal to the optimal. We can also, because this is so general, learn distributions for multiple samples to be drawn at once. So in this case, we've trained it to draw 3 different samples at the same time, and it learns that you should keep these samples separate or far away from each other, as in kind of this low dispersion result that we had earlier, that when you draw samples, they really shouldn't be close to each other. You should kind of leverage the structure there. And these light colored ones are the results for learning 3 samples at once, and it just slightly bumps up our success rate. But for things like this, it took us from 85% to 95% success at very few samples. So this could also be extended to learning 100 samples at once, or even more samples. We just wanted to try it with a low number, but I think that's an area that we can look. In terms of use on other systems, so for a humanoid robotic system, we can watch it just run around. And these are samples drawn from our conditional variational autoencoder. These are samples drawn, or this is a sample drawn randomly. This is one of the better ones. They're mostly crazy, which, to be fair, you wouldn't usually use sampling-based planners for this type of system. But we hope that by learning these distributions and improving our samples, that maybe we could in the future. We also learned from human demonstration on a multi-robot system. So we have these 2 cars performing a lane change maneuver. We have a lot of data from people actually driving the cars and doing the maneuver. And we learned 2 separate distributions where, they basically stay in their lane and then perform the lane change. What's also interesting and could be difficult to see, but is that it realizes that this one is going faster. So most of the samples here actually have the blue behind, so passing behind the red car. It also never has them on top of each other. So it's basically learning a distribution of exactly what we'd expect for a lane change procedure. And then we applied it to a satellite, basically doing debris recovery. It has a double integrator body and then 2 kinematic arms. And we saw the same convergence and cost even for this 12-dimensional system. So now I'm going to go on to how we can leverage GPUs for real-time motion planning. So as robotic systems move into the field, so something like a delivery robot, they're in this kind of sense and react paradigm where they need to sense their environment, build some SLAM representation, plan an algorithm, and then plan a trajectory, and then control along the trajectory. So this happens, you might get a point cloud at 100 hertz, you're processing it maybe locally at that 100 hertz, and then building your environment again every 10 hertz. This we replan maybe once every second, once every 5 seconds, and then our controller runs at 100 hertz, 400 hertz. So we've got 100 hertz, 1 hertz, 100 hertz. So we really want to focus on speeding up this planning algorithm so that we can plan within that loop. So we can plan, all of our plans have the most recent information about where we are, what the environment looks like. So we might be able to just wait until computers get faster. That's worked in the past. But it turns out that we're starting to see some leveling off. This blue curve is the single thread performance, starting to level off in time. And instead, what we've started to pick up are a number of logical cores. So we're falling back on parallelism to speed up our computers. Essentially, if you have tasks A, B, C, and D, instead of doing them in order A, B, C, and then D, as long as they don't depend on each other, we can do them in parallel along different threads. If we take that to some limit, we get graphics processing units, or GPUs, which essentially, I mean, they were born out of the graphics industry. If you think about computing an array of pixels, each computation for the pixel is independent. So we leverage thousands of very simple cores to do the same instruction on a bunch of data, and it can be done simultaneously and speed up orders of magnitude. We can also use this, though, for general purpose computation. So as long as you can structure your problem in such a way that you can leverage thousands of cores and that you can limit the divergence of threads, so limit any sort of, if this happens, then a thread has to compute this, and else it goes somewhere else, because then it has to wait for the other threads in its group to complete. So why hasn't this been applied too much to motion planning? Well, it turns out motion planning is an inherently sequential problem. We're basically trying to find a sequence of actions, which means to define the next part of the actions when you're exploring the state space, you need to wait for your trajectory to have gotten there. You need to have explored. We can do something like probabilistic roadmaps. That's actually embarrassingly parallel. So building that graph where you're just looking at local nodes and then looking in the region, that can be spread out over the entire, over a GPU. But if I were planning in, say, the Durand building, and I want to go from here to just get coffee back there, instead of building a graph of the entire Durand building, I'd like to explore in the area that matters to my planning problem. So to speed this up, a lot of people use, they build trees throughout the state space. In this case, I'm going to discuss fast marching trees, which was out of our lab a few years before me, using lazy dynamic programming. So essentially, starting with some tree that's expanded through the state space, you find the minimum cost node in the edge of the tree. You then look in that neighborhood for any nodes that have not been explored and try to connect them to the tree. So doing dynamic programming as you build your tree throughout the state space. If you try to connect a node and it fails a collision check, that's where this lazy comes in. You just move on, and you'll try it again another time when it's in the neighborhood of an expanding node. And this turns out it reduces the number of collision checks that we require and speeds up the algorithm. Unfortunately, dynamic programming is again sequential, and we wanted something massively parallel. Something that people have done in the past have used and parallelism with existing algorithms. So as I mentioned with probabilistic roadmaps, just assigning a node to every single, or assigning a thread to every node, or parallelism, where you could run a bunch of rapidly exploring random trees, and the first one to return, or the best one to return, is what we keep. And then others have parallelized subroutines, like the collision check can be parallelized fairly easily. This doesn't give us really the orders of magnitude speed increases that we need to get to where we want. We really want to build an algorithm from the ground up with parallelism in mind during the search. So taking inspiration from the fast marching tree, we use lazy approximate dynamic programming. So we're essentially exchanging exactness for parallelism. In this case, instead of doing a minimum cost node expansion, we expand a bunch of nodes within the tree, within the edge set of the tree that are all low cost. So anything within, say, this ball radius is going to be expanded together. And that means that we can process those in parallel, we can process any neighbors that we found that were unexplored in parallel, and slowly build our tree outward in this kind of wavefront fashion. And you can also, depending on how fast you want to expand the low-cost ball radius that you're allowing to connect, or allowing to expand, you can control how parallel you want to be versus how much optimality you want to lose. So at one end, you could expand it extremely slowly, and it's basically just dynamic programming, expanding just the minimum one at once. On the other end, you could expand it extremely quickly, and it gets closer to a breadth-first search. So we're expanding these groups and marching them throughout the state space, giving us the group marching tree algorithm. I've color-coded in this plot basically all the samples that are expanded in parallel. And for this 2D example, you can see there's maybe hundreds that are expanded in parallel along the wavefront. So this is a whole wavefront, but you also get some of these are all part of the same parallel wavefront. And that gives us some massive parallelization over the sample set. For the 2D, it's maybe hundreds, but as we get to more complex problems and higher dimensional spaces, this can be thousands expanded at once, so we can fully fill the GPU. We also still leverage this idea of lazy collision checking. So if we try to connect an unexplored tree to, or an explored node to the tree and it fails the collision check, we just move on and we'll try on the next wavefront. And finally, instead of using a minimum cost heap, which we'd have to do, or ideally do to find the minimum cost node for each of our expansions, we can just put these nodes, we know once it's been added to the tree set on what iteration it's going to be expanded from. So we can just put them in cost thresholded buckets, which are a lot more parallel of a data structure. And finally, I said we lose some exactness. It turns out we can provably bound that suboptimality. In practice, we can also look at how much we lose that suboptimality. So this is a scan of the Gates building. Its entire floor. It's about the limit of what you might consider for sampling-based motion planning usually. And we first see we only lose about 10% of suboptimality. This is with the most aggressive, most parallel version of the algorithm, where we're really expanding the wavefront as quickly as possible. We also find that we can solve it in about 10 milliseconds on a GPU, or 30 milliseconds on an embedded GPU. This represents about 100x speed up over the state of the art. And it's also this 30 on an embedded GPU. This is like a little credit card size machine that can be put on a quad rotor. It turns out because this algorithm is so lightweight and that it combines when it's exploring the state space with solving the planning problem, that we can actually put it on one of these systems. And instead, like probabilistic roadmaps, which is embarrassingly parallel, is so heavyweight that we barely, we might see a speed up of 10, but if you put it on an embedded GPU, it's pretty much the same speed as with the CPU algorithm. Here we're still seeing, 30, 40x. Now we wanted to show some system where this might really matter. So we have this problem where it's inspired by a collapsing cave. We have a quad rotor in a cave system, basically a maze on the bottom, and then a couple connecting tunnels, and it wants to escape out to here. And we have obstacles coming in at varying rates as the environment degrades. So as the cave collapses faster, that's what this axis is. And then we're also disturbing the system, so having some disturbance on the x and on the position and the velocity. And this is increasing disturbances. And these are all just success rate of how many times out of 50 that it was able to make it out of the cave system. For fast marching tree algorithms, this is replanning about once every second. We see what we would expect as the disturbances increase. We start to fail more and more frequently. As the environment degrades faster, we fail more and more frequently, eventually down to 0. And then we have but with the group marching tree algorithm doing 100 hertz, first of all, disturbances seem to barely bother it. So as it's knocked around, it replans with the new localization that it has, or with the new velocity that it has, and is able to still escape fairly easily. As the environment degrades faster and faster, it also kind of gracefully fails less often. And it's important to note that even at this part, it may not be possible in some of these ones for it to escape. Very quickly on, all of these tunnels could be blocked and then it just can't get out. So I don't know what the upper bound of what percentage it could have escaped is, but this is obviously a lot better than replanning at something like 1 hertz. Oh, and I have a video. So this is at a quarter speed because PowerPoint couldn't do the 100 hertz that I wanted. But you can see basically here an obstacle got in its way and it replanned and was able to successfully turn back around and not be in collision. And there's a lot of, you can see some of the shakiness that's basically from it being perturbed around by the disturbances.
Can you describe what is exactly being redone at each time step?
So it's replanning the global planning problem.
Completely from scratch and not maintaining any samples from the previous? So
I've pre-computed, or I've computed a graph, and it is replanning on that graph, but it's doing all the collision checks.
All the edges are?
All the collision checks, all the free space, or all the checking if the samples are free is doing that online.
Is that necessary?
So yeah, I could have optimized it even more and said, it's a collapsing cave, it's not gonna, nothing's gonna free up. Though in practice, maybe something could free up. So I just kind of wanted to show, maybe it opens up a hole. I just wanted to show kind of even without working too hard on this problem, we're able to get these benefits. Okay. So I'm going to talk about how we can leverage GPUs in order to get robust motion plans. So we might have a traditional motion planning problem assumes deterministic, perfectly known systems that are going to follow a trajectory well. It works really well for this robotic arm. We have this trajectory that pretty narrowly cuts the corners, which is exactly what we want. It's near optimal. But if there's any uncertainty, if we're flying a quadrotor like this and we have uncertainty in the control and the localization, that might propagate like this plan turns into a nightmare. It might crash 90% of the time. So what we want to specifically look at is the stochastic hemodynamic motion planning problem, particularly meaning a low-cost trajectory that's dynamically feasible, subject to a separate constraint on the collision probability. So we want to bound how often this is going to collide. To pose this more mathematically, we want this minimum cost path with a probabilistic bound on what likelihood it's going to crash, and then with, in this case, LQG dynamics and measurement. Some previous approaches, one is to formalize it as a POM-DP. As the problem becomes more and more complex, this kind of blows up and doesn't really work for a lot of the planning problems that we're looking at. We can also compute a bunch of open loop trajectories and then just say which one's the most robust. It turns out that if you don't consider robustness during the planning process, even though you might have 1,000 different options, none of them may be robust. If it didn't actually stay away from walls and if it didn't try its best to be robust during the planning process, you end up with things like 20% collision probability, which isn't really feasible for what I would call a robust motion plan. And then Monte Carlo motion planning, which came out of our lab, used a safety buffer, so stay farther away from the walls as an analog. It turns out, I mean, this works pretty well, but if I were here and I want to go here, and in front of me is this narrow passageway, but like a narrow door, or I can go all the way around a big hallway. It turns out most of the time I probably want to just go through that narrow passageway. So I get closer to the wall, but it's a much shorter path. It exposes me to less risk. So what we really want are plans that can be computed still in real time, that are globally optimal, so still solving from A to B, with low collision probability. So we want 1%, 0.1%, 0.01%. We don't want to have to, target these 10 and 20. We'd also like to certify, provide some certificate that we do satisfy this collision probability constraint. And we'd still like high performance trajectories. We don't want to have it just very slowly move through the world. We want to push this to the limit of safety. So this last one's kind of the key here, that the solution should lie somewhere on the Pareto front of cost and the collision probability. So we should just directly search that Pareto front using a multi-objective search. Unfortunately, this also adds some computational burden, so we'll just offset that with the GPU by structuring our algorithm in such a way to use it. And then to compute the exact collision probability as we explore the state space, we might be considering a bunch of paths. It turns out it's pretty computationally intensive to do something like Monte Carlo, and it's rare that we would have some exact analytical solution for the collision probability. So we're going to use an approximate collision probability, which we propose a new method that's massively parallel, but I'm not going to go into too much detail on that here. And then we use that when we search the state space, and then we later certify the best paths subject to Monte Carlo. So it's the Parallel Uncertainty Aware Multi-Objective Planning Algorithm, or PUMP, which begins by massively parallel sampling-based graph building. So this is similar to probabilistic roadmap, building a map of the environment. We then do a massively parallel multi-objective search to identify the Pareto set of solutions in terms of an approximate collision probability and a cost. Basically, the idea here is to identify a bunch of very promising solutions that we can then search over that much smaller set through a bisection search and then certify our plans through an exact collision probability estimator, so Monte Carlo. And then if there's any leftover aggressiveness, like it's a little safer than it needs to be, we can smooth out our dynamics until it's right against the limit of them. So a 2% collision probability path might go around the outside, take this more circuitous, slower route, whereas a more aggressive one can go through the middle, give us a lower cost, but is a little less safe. So it's, in terms of performance, so we planned for a 0.1% collision probability here, a 2% and a 5% here. It turns out with the noise we were using, you couldn't really do lower than the 2% in any of these, just the solution didn't exist. And we were during our multi-objective search, able to identify pretty much all the important homotopies of the problem. So we identified this whole set of Pareto optimal paths that encompassed most of the options of how you could explore the state space. And then we can do this bisection search just over that really small set, and we end up with solutions that are right against the collision probability constraint. That's this line. So they're basically as aggressive as they can be within the safety constraint. And then this only took about 100 milliseconds for a lot of these planning problems, during which time, during the multi-trajectory search, it actually evaluated hundreds of thousands of partial plans. So it evaluated them with this approximate collision probability, and then certified only tens of plans using the final bisection search and Monte Carlo method. If we want to apply this to sort of a system that we might see in the field, look at perception-aware motion planning. So field robotic systems often need to learn an environment through simultaneous localization mapping and then localize themselves within it. In this case, we're looking at the Google Tango system. Essentially, it's this cell phone that has a fisheye lens that's picking up features through the world. It's got an IMU, which is then fusing with the movement of the features for visual inertial odometry, and then it's got a depth camera that it's able to use to do SLAM on, to actually build the environment. And a lot of the environments that it builds might look something like this. And as you just quickly looking at it, it's not really uniformly explored throughout. And so you're not going to be able to localize yourself as well throughout. So we really want trajectories that are going to be able to localize themselves well, given a perception system. This might be we didn't learn it there, or it could be darker and less feature-rich, that kind of thing. Unfortunately, it's pretty difficult to actually compute ahead of time how the uncertainty in the perception is going to go. So we have some drift, we have nonlinearities like loop closure, and just in general, these systems are pretty complex within the environment. So first, what we did was we got a bunch of training data of a robot moving around, which this was my best robot operation. And then we use that to train a model, a learned model that will predict the error rate. So essentially we take in what our sensors gave us. For this work, we used the number of features that it could see given its pose in the environment. We then learned a model of the error rate distribution, and we actually fit it pretty well. In this case, red is the true and blue is the predicted error rate. And so what we're saying is we can predict, well, if you go do this, you're going to delocalize, or you're not going to be able to localize as well along that path. To put it in test, we designed this environment within our lab where if you go to the right, it's pretty feature-rich. There's pretty structured windows. There's a lot of clutter over there that it can pick up features that it can count on. If you go to the left, though, there's these white sheets that we put up that are both pretty feature poor, and they're moving once the quadro is going through, kind of buffeting them. We plugged a Google Tango phone on the front of the quadrotor, and then we learned this heuristic through our environment. So it does depend on which way you're looking, but this is just to visualize that it actually learned the areas that it cares about. So over here in blue, we localize well. If you go to this corner, you're going to have a lot of trouble. And then we planned a perception agnostic path, which is the faster path, and then a perception aware path that goes around the outside, but not only goes around the outside, but is looking outwards towards this the entire time, towards a better feature area. And once we planned it, or once we ran it, we had the perception aware path succeeded every time, really had no problem. Whereas the perception agnostic path crashed 3 out of 13 times, so about 25% of the time it crashed, resulting in things like this, and eventually to the point where it was crashing so much that I had to go in there with a lacrosse helmet and a pillow to catch it, because we were going to lose our quadrotor if it crashed catastrophically. And so what this looked like, what it could look at, I don't know where my mouse is. All right, we'll just watch the whole video. So you can see basically it planned from here and went around, and the perception aware path is going to be looking at pretty good features the whole time. And it's starting on this side of the sheet, so it was faster to go that way, but. And then I'll show so first of all, you can see that these sheets are kind of buffeting, resulting in pretty poor features for localization. And this slight movement is going to really throw it off. And then we'll get a view of what it looks at when it's. So it's seeing these pretty much no features to really pick up on. So it needs to learn that flying that trajectory is not going to be as successful. And it turned out also all those crashes were due to lost localization. You can actually see where it thought it was and where it was truly with a Vicon system, and they pretty much would diverge off the path. So in conclusion, First, I showed that using de-randomized algorithms, so de-randomizing these algorithms with deterministic low dispersion sampling sequences gives us some deterministic theoretical guarantees. It lowers the computational complexity and improves practical performance. And that was before even considering things like it trivializes nearest neighbors and may help towards certification. Then we learn sample distribution, so instead of uniformly sampling the entire state space, we can actually learn this conditional distribution of a problem and focus heavily in that region while still maintaining the theoretical benefits of the earlier work. Then I talked about real-time motion planning by leveraging GPUs. So GMT allowed about 100 hertz planning, even near that rate on an embedded credit card sized GPU. And then the I guess parallel uncertainty aware multi-objective planning algorithm had certifiably safe paths in about 100 milliseconds, right up to the limit of our safety. And then I showed how we can use this multi-objective approach by replacing, instead of the approximate collision probability, we can just replace it with this learned heuristic that encourages good perception throughout the route. So in the short term, towards sampling strategies, we did test it with dynamically constrained systems and just used a lattice, but it turns out that the optimal low dispersion sampling sequence for a lot of problems may not be a lattice. So I think there's some interesting work in how do we actually define a good low dispersion equivalent in terms of the reachable set instead of in terms of just a spatial lattice. Also looking at learning sampling distributions online. So say we have a robotic system operating in a hospital over months. We'd like to be able to learn how it moved to the hospital in order to encode some things like preferences. So maybe it needed to stay to the side of the hallway because people were often blocking it. Or to learn things like semantic information. So this doorway or this hallway is a good thoroughfare to go through. And then finally, some work, in terms of sampling strategy, some work that I've already started is planning in learned latent spaces. So a sampling-based motion planner really just requires these three algorithmic primitives: the probing samples, connecting to nearest neighbors, and then a collision check. If we can encode all that into a lower dimensional state space that may exist for a lot of planning problems. So in this case, I have this robot that's basically just a point, and we're planning within the visual space. We can actually learn a lower dimensional representation in the latent space and then do all these primitives within it. We also need to learn a collision checker, but in terms of what the nearest neighbors are, we actually encode that within the latent space, and we are able to plan. Well, I might not be able to play this video because I don't know what the cursor is.
The cursor is on the projector.
Oh, so it's just not on that. Okay. I've just been moving it around. So basically, just having seen this robot move through the world and what it couldn't collide with, and it's just this like pixel space, 200 dimensional system. We actually learned that to get from here to here, the fastest route is going to be right along the border of this obstacle and then cutting up. And then in terms of massive parallelism, using GPUs and robustness, I'd like to look at other multi-objective planning problems. So maybe we want to leverage, or we want to look at having a aggressive trajectory that still maintains some level of passenger comfort in a self-driving car. Or here this self-driving car is actually stuck because there's some construction and it's confused and it's completely paralyzed there. Maybe we want to look at finding a low-cost trajectory, and the second objective is how much you break the rules. And ideally, if you can find a trajectory that doesn't break the rules at all, that'd be perfect. That doesn't go in a lane at all. But the second that fails, maybe we can fall back on these still safe trajectories that slightly violate or most minimally violate the rules. And then finally, expanding some of these field experiments to look at more realistic uncertainties and really see if we're able to capture them well to then put into things like pump. In the long term, I want to look at robust operation. So I was recently part of a panel that was discussing robust operation for robots and talking about walking up a ladder. And someone was mentioning that it's very important that if you reach for the ladder and you barely miss the step and you slip, that it's robust enough to this disturbance. I think we can approach this from the planning problem where ideally you're never trying to step just to where in a position where you could barely miss the ladder. You should really be planting firmly in the middle of it. And if we encode this during the planning process, we can get a lot better operation there, and hopefully that robustness kind of goes through the whole stack. Also, we got orders of magnitude speed ups with GPUs, but also looking at FPGAs and other domain-specific computing. There's some work being done on specifically chips for collision checking, which I think has sped it up maybe like 3 or 4 orders of magnitude even. So designing chips specifically for our algorithms, or designing our algorithms around those chips, I think will be very important. And then certifying planners. So given these deterministic guarantees, we might be able to say, if this is what our problem looks like, or our problem has a solution that has this much room, we can guarantee that in this amount of time, certifiably we'll be able to solve it. I think that's an important step towards deploying a lot of these things in the real world, being able to certifiably guarantee that you will solve the planning problem. And then robotic learning has, at least in research, taken a lot of us by storm. And I've leveraged it in some of this work, but I think it's important to maintain some of the theory behind that we've developed behind it. So still giving guarantees while exploiting some of the robotic learning. So that's it for my talk, and I just want to say thank you to my whole committee. Those of you that I've talked to a few times during this process, I think your feedback's been great and really appreciated. Some of you I've actually taken classes with, and that's been wonderful. Professor Rock, before I came here, I hadn't done any controls, and I was actually in fluids. And I took your class and I loved controls, and that was a big reason for me to switch. And then specifically Marco, thank you for taking me to your lab, giving me a lot of freedom to work on my ideas, but also making sure my ideas are well-founded and actually important. I think I probably would have gotten lost in the weeds in a lot of things if it weren't for you really pushing me along. And then always just telling me to make papers better. I think I'll forever remember just the words "keep polishing" when we're a week out of a paper deadline and the paper I think is done. And I keep working on it, and hopefully they've become better and better and have pretty big improvements. To my co-authors, particularly Ed, I think he's on most of those papers. Thanks for answering my questions and helping when I begged you enough. And then James, Lucas, and Benoit, having these conversations with you and working with you has been great. And then these are actually from my undergrad, my Professor Eric Loth and Dr. Adam Steele, who I think laid some of the foundations for how I research, and yeah. And then to my funding, particularly NDSEG, which gave me a lot of freedom to kind of move around and particularly focus within robotics. And then to my friends for, I don't know, all the adventures that I've had throughout. I think I probably would have been done faster, but I wouldn't have enjoyed it as much. To my car that made it within a week of being done, and then a snowplow got it. The ASL for putting up with me in lab and just having these discussions, both the old ASL and the new ASL. And then my family, who has also supported me the whole time along the way, but let me kind of define my own path. I think, so this is a picture of us at the eclipse, which my family's pretty enthusiastic about, and I think it's clear that maybe my field is no coincidence given that background. And that's it. I guess we'll do questions if.
I think on one of the algorithms you said that it can identify the homotopy classes.
Mm-hmm.
Would knowing the homotopy classes beforehand, could that benefit?
Yeah, so I mean, if you had some idea of what all the homotopy classes are, you might even be able to use, some people use trajectory optimization in order to solve these problems. So setting up the whole problem is a just optimization problem. And the problem with that is it doesn't give you any global solutions. It's just going to stay within the local of whatever your initial guess is. So you could run something like that, which I haven't compared against, but could perform similarly. Yeah.
At the very beginning of the presentation, when you were showing some of the advantages of using the low dispersion sampling, and there were two cases, I think, that had slightly worse performance. Is there something about that problem structure, the low dispersion sampling? Is there any problem structure?
So in this case, I was just showing a lattice, so a grid structure. And so one problem that can occur with something like that, which instead you might want to use something like Halton sampling or perturb the points around, but is that they have this underlying structure, and so whole rows of points can be wiped out at once if the wrong obstacle is in there. So there can be these pathological cases against something like that, because that's where you might want to embed some amount of randomness or some other sampling sequence that doesn't have the same amount of structure. And I think that's what happened in those 2 problems. Even still, it was barely. It can also, the random gets I think 100 tries and then, or 100 different problems. It gets 100 different randomly generated samples and it converges to some number. If it just gets unlucky with where the samples are placed for the lattice, then it doesn't have a chance to kind of converge to some mean. It can be on the outside of the variance of it.
Any other questions from the audience? I guess. If not, should we do it? Let's thank you again.
Thank you.
Yeah, 5 minutes break.